This is Daniel Creasberry, and in this lecture, we're going to be looking at operations with rational numbers. So we're going to be doing things like adding, subtracting, multiplying, dividing, and maybe doing a problem or two involving fractions, rational numbers. So let's go ahead and start. First off, multiplying is probably one of the easier things to do with rational numbers because multiplying works exactly as you should expect. So if we have 3/8 times 7 over 11, the way you would multiply these numbers is you would multiply the numerators together and write that as the numerator, so 3 times 7, and then you multiply the denominators together, 8 times 11, and that will be your denominator, and this is your answer. So multiplying rational numbers is that straightforward. You multiply the numerators, multiply the denominators, and we'd look to see if there's anything to simplify here, and I don't see there's no sort of common factor, so this will be our answer. So we can do the same thing with negative numbers if we wanted to. This is negative 2/3. And notice how it's written kind of in parentheses, so the negative signs stick out, times negative 9 over 4. And since we're multiplying two negative numbers together, those negatives actually cancel, and you end up getting a positive answer. So if I multiply the 2 and the 9, I get 18 as the numerator, and 3 times 4, I get 12 as the denominator. And again, the negatives cancel out. And so here, I've got a number that has common factors, so maybe we can reduce this. These both have a common factor of 6. So if I divide 18 by 6, I get 3, and if I divide 12 by 6, I get 2. So this is my final answer. It's nice and reduced. We can also multiply together mixed numbers. So here are two mixed numbers here, and to be honest, the best way I found to multiply these mixed numbers together is to first write them as improper fractions. So we don't have this whole number part and fraction part. We just have just two fractions we're multiplying together. And then it ends up looking a lot like these examples A and B where you multiply fractions. So I'm going to do that. For one, let me rewrite 2 and 4/5 as, let's see, if I multiply and then I add, I end up getting 2 times 5 is 10, plus 4 is 14 over 5. So that's that first number written as an improper fraction. The second number is 3 and 5/8. And if I do the same, I multiply here and then I add here. I get 3 times 8 is 24, and then add that to 5, I get 29 over 8. And now I have two improper fractions that I can multiply together. So now I'll do the multiplication. 14 over 5 times 29 over 8. And now I can multiply the numerators and multiply the denominators. I'm going to use a calculator on that. 14 times 29. And I get 406 in the numerator, and I get 40 in the denominator. Now it looks like those two numbers have common factors. They're both even, so maybe I'll divide them both by 2. And on the numerator, I end up with 203. And in the denominator, I have 20. And I think that's as simple as that can get. So that's how you multiply mixed numbers. I suggest turn them into improper fractions first and then do the multiplication. And then it works the same way. Dividing rational numbers is almost as straightforward. There's only one little catch, is that when you divide mixed numbers, and it's kind of summarized right here, all you do is you change this division sign to a multiplication sign, and then you flip the second fraction. So here you see it's written as C over D. You want to flip that to D over C and do multiplication instead of division, and then it works out the same as those last few examples we did. I like to call this, there's a little common saying, we call it keep, change, flip, or KCF, where you keep the first thing the same, so that A over B, you change the sign, and then you flip the second fraction. So you change the division to a multiplication, you flip the second fraction, and then if you do that every time, it works just like a multiplication problem. So we can do this here. We can take this problem, and we keep the 5/8 the same. We change the division sign to a multiplication sign, and then we flip the second fraction. And now this becomes a problem just like in example 9. And that is our answer for that one. So again, it's almost as straightforward as multiplication. You just got to do that one change first. So we can do the same thing with mixed numbers. Let's do what we did in that last example, and first write them as improper fractions. So I'm going to multiply 1 times 4 to get 4, and then add it to 3, so I get 7 over 4 for that first mixed number. I'll do the same thing here. I'll multiply 2 times 8 to get 16, and then add it to 5 to get 21. and the denominator stays the same. So now that I have my two mixed numbers written as improper fractions, I can do 7 over 4 divided by 21 over 8. Then I'll keep change flip. I'll keep the 7 over 4, change the divided by sign to a multiply sign, and then write this as 8 over 21. And this gives me 56 over 81. Now, there's some common factors in there. Sorry, that's 84. In fact, those two numbers are both divisible by 4. So if I take 56 and divide it by 4, I get 14. If I take 84, divide it by 4, I get 21 again. And it looks like there's still some common factors. I didn't notice there was a 7 in here too. So we divide both those by 7. We end up with 2 over 3. So you've got to reduce it until you're done reducing it, which this is a fully reduced fraction. So there's division, works just like multiplication with that one exception. Adding and subtracting rational numbers is a little bit messier because you can't just add the tops and add the bottoms like you do with multiplication and division. Adding and subtracting rational numbers only works when you have alike denominators. So this first example is pretty simple because the denominators are exactly the same. So when this happens, we can simply take the numerators, the 7 and the 5, and do regular subtraction. So this is equal to 7 minus 5 over 12, which is 2 over 12, which we can reduce to 1 over 6. So adding and subtracting is straightforward as long as the denominators are the same. Unfortunately, in most cases, the denominators aren't the same, so we're going to have to do some extra work in order to make that happen. So when we have different denominators, we can still do the addition and subtraction, but we can't just start here. We've got to start by changing the denominators to a common one. We're going to find what's called the least common denominator, which is the smallest multiple of the denominators that they have in common. So if we write out, there's a few ways of finding the LCD. The one I like involves writing out the multiples of the denominators, each one. And we're going to write down as many as we can until we find one that they have in common. So for example, I'm going to do the 31st because it's easier. The multiples of 30 are 30, 60, 90, 120, and we can keep going if we wanted to. But the idea is we want to write out as many until we find one in both of these rows that are exactly the same. So the multiples of 24 are, of course, 24, 48, 72, 96, then 120. So there it is. We found the multiple that they had in common. The first number that showed up in both rows is 120, so that's the least common multiple, also called the least common denominator because we're dealing with denominators. So now that we found that, we want to transform both of these fractions, both of these rational numbers, into fractions with a denominator of 120. Okay, so to do that, let's just start kind of with 5 over 24. And I'm going to kind of try to do this all in one line to see if I can save some space. I'm going to leave a little space here. But we want to multiply 24 times whatever number will give us 120. Okay, so it should be a number, you know, and we can find that from this list here. So this is 24 times 1, 24 times 2, times 3, times 4, and times 5. So if we do 24 times 5, we get 120. And then we know if we multiply this fraction by one number over itself, so 5 over 5, we haven't actually changed the number. We've just kind of changed how it looks. So this is what we're going to do. We're going to multiply the numerator by 5 and the denominator by 5. So we're not actually changing the number. We're just multiplying by 1, essentially. And we'll do the same thing here. So we want to multiply 7 over 30 by some number over itself so that 30 becomes a 120. Okay, so these are the multiples of 30. We multiply 30 times 1 to get that, 2 to get 60, 3 to get 90, and 4 to get 120. So 30 times 4 is 120. And then we got to multiply the numerator by 4 also, so we're not changing anything. This problem's a little bit more work than the last few we did. So now that we know that, we can do the multiplication. So the first number becomes 25 over 120. The second number becomes 28 over 120. And then I can do regular addition in the numerators now that I have a common denominator. So I can do 25 plus 28, which equals 53 over 120, and that is my answer. We can also add and subtract mixed numbers with unlike denominators in a similar fashion. For these, I prefer to kind of set this up as maybe a typical subtraction problem where we line up the parts of the number that they have in common. So for example, I want to line up this 5 1/4 minus the 2 2/3 so that I can see my whole number parts over each other and my fractional parts over each other, and that way I don't get the two confused. And hopefully that helps me do things well. Now what I need to do first is I need to change my denominators so that they're both common denominators, because I got a 4 and a 3. The least common denominator of 4 and 3 would be 12, and so I'm going to multiply these fractions by numbers that give me 12. In this case, I'll multiply the bottom by 4 over 4 and the top fraction by 3 over 3. And once I do that, I get this top number is going to be 5 3/12, and the bottom number is going to be 2 8/12. And now I have somewhat of a conundrum because the fraction part on the top is smaller than the fraction part on the bottom. So there's a question of, well, what do I do? Well, I mean, I could go ahead and start doing subtraction, but what's going to be nicer is if I turn this problem, well, I can do a method that I usually do when I subtract, when the stuff on the left there's stuff on the left, but the stuff on the right is not quite as big as the stuff on the bottom on the right. We're basically going to borrow one whole part of this whole number and move it over to the fractional part. So what I'm going to do is I'm going to take away 1 from here, so take a whole part away. So now I only have 4 whole pieces instead of 5. And I'm going to turn that whole part that I borrowed into 12 pieces. So I have 3/12 already. I'm going to add 12 more here to make this 15 over 12. So this is the idea of borrowing, where I take away a whole part and I move it over to the fraction part. So I just moved it. And now I have the number 4 15/12 that I can use to subtract. Now that I've done this, the subtraction part is going to be really easy. I can take 15 minus 8, and that becomes 7/12. And then I can subtract the whole parts, 4 minus 2, to give me 2 whole pieces. And this is my answer. That 7/12 doesn't simplify, so I'm done. So again, it's this idea of borrowing that you've done when you subtract numbers regularly. Something similar might come up when we add mixed numbers. So I'm going to start by writing this out so that my whole number is over my whole number and my fraction is over my fraction. Sorry for the messy numbers. And I want to add, but before I can really add, I've got to change these fractions again. So I've got a denominator of 3 and a denominator of 4. So I'm going to put them over the LCD, which is again 12. So this problem becomes 2 8/12 plus 1 9/12. And now I can do the addition. So let's do addition. I can do 8/12 plus 9/12 gives me 17/12. And 2 plus 1 gives me 3. Now, I would be done, except I'm working in mixed numbers. So since I have a mixed number, I don't want to leave this improper fraction part here. So I can kind of do what we usually do in addition when we end up with a whole bunch of stuff in one column that can really be transferred over. Is I'm going to take a whole piece from here, so 12/12 from here, and turn it into a whole part. So just move it over to the whole number part, and then I'll have some fractional stuff left over. So when I do that, I actually end up with another whole number, so I'm moving 12 over, and then I have 5/12 left over. So that gives me a really nice looking answer without an improper fraction here. So that would be the end of that problem. Now that we've done addition, subtraction, multiplication, and division, we can talk about order of operations with rational numbers. This is going to work just the same way as order of operations, where we're going to abide by please excuse my dear Aunt Sally. So I'm going to look for any sort of parentheses and exponents first. And this is a really helpful example because we have a fraction here and then some stuff going on in the numerator here. And whenever you see any sort of multiplication or addition or subtraction in a numerator or denominator, we're going to treat this as though it has parentheses around it. The way it's written is we should do this subtraction first before we do the division. Even though you don't see actual brackets or parentheses, we're going to pretend like there are. So that's going to be the first thing we do. So this problem might take a while. We'll do 7/9. Let's go ahead and change that 3 into something over 9. In this case, it's going to be 27/9, 27/9. And then we're going to divide it by 5/6. We're going to divide by 3 seconds, and then add 3/4. So that's the first thing we want to do, is this subtraction. So when I do it, I have 7 minus 27. That gives me -20/9 divided by 5/6 divided by 3/2 plus 3/4. So now I want to proceed to do the division, and the way the order of operation works is I should work from left to right. If I see several multiplication signs or division signs, I should do the one on the left first and then start working my way to the right. So I'll ignore this one for now, and I will do this division first. So in order to do this division, I'm going to keep this first fraction the way it is. I'm going to change this division sign, because that's how we do division. We change that to a multiplication sign. And I'm going to flip the second fraction. So this is going to end up looking like -20/9. This is my keep part. And then the division sign changes to multiplication, and I'm going to multiply by 6/5. I flip that denominator. And then I'm just going to write everything else. This is going to take a good long while, I think. Gotta love order of operations. So now I have multiplication and division. I'm still going to start from left to right and do this multiplication. So I have -120 divided by 45 divided by 3/2 plus 3/4. And before I do that division, I'm going to simplify this so that my numbers get smaller. I think I have a factor of 5 in both of these. So I can divide both these numbers by 5. I'm doing that in my calculator real quick. So 120 divided by 5, I get -24/9. And then I'm going to go ahead and change this now. So let's change that to a multiplication sign. And then add 3/4. That'll be the last thing I do because it's addition. So now I can do the multiplication. I get -48/27 plus 3/4. We can reduce this a little bit because there seem to be factors of 3. I think just a factor of 3 in this. So if I do 48 divided by 3, I get -16/27 divided by 3 is 9 plus 3/4. So now we're down to an addition problem. This sure is a long problem. Okay, we want the least common denominator between 9 and 4, and that denominator is 36. So I'm going to do -16/9 times 4/4. And then I'm also going to do 3/4 times 9/9. And I end up getting, what number is that? Get -64/36 plus 27/36. You do that addition. Hold on. I get -37 divided by 36 as my final answer. So that problem was a little long just by nature of the fact that it had a bunch of fractions and operations in it. But I hope that was helpful as far as keeping track of what you need to do at what time. Just remember that please excuse my dear Aunt Sally, and this is really helpful to kind of look at too. There's a couple more things in this section. One property of rational numbers is what we call density, which means that if you have any two numbers, rational numbers, there's always some number in between them. So if you were to like write these out on the number line, and maybe there's a 0 here, maybe this is 1/4, and maybe this is 1/3. The fact that the rational numbers are dense means there's a number in between these two. So you can give me any two rational numbers and I can tell you a number between them. And so this example, we're actually going to find a number that's halfway between 1/4 and 1/3. And we know it exists already. We're just going to find out what it is just so we can show you kind of it's there. So to find any number halfway between two numbers, we're just going to add these two up and divide by 2. It's kind of like finding the midpoint. And once we do that, we'll have that number. So to do that, let's change these two numbers over the same denominator. So this should be 3 over 12. The 1/3 will change into 4 over 12. And I'll just leave this over 2 down here. So remember on that order of operations example, all this stuff going on above this division bar is going on in these imaginary parentheses. So we're going to work all this out before we divide by 2. This ends up being 7 over 12 divided by 2. Oops. And now we can simplify this now. So this is 7 over 12 divided by 2, and you can even think of this as divided by 2 over 1. And I wrote that in there so we can rewrite this problem. So this is 7 over 12 divided by 2 over 1, which is really 7 over 12 times 1 over 2, which is 7 over 24, and that's my answer. So that's the number that's halfway in between 1/4 and 1/3. And so the idea that the rational numbers are dense means I can give you any two fractions and you can do what I just did. You can add them up, divide by 2, and get a completely new number that's halfway between the two you started with. So, if you're into that sort of thing, that's kind of cool. Let's look at one last problem. It's a word problem that involves rational numbers. It's extremely practical. We've got a board. Here's my board, and it's going to be 3 feet long. There's my little tick mark for feet. And this says that the board is cut that's 7.5 inches long, cut from this whole board, and so maybe it's cut right here. And this piece is, I'm sorry, I said it wrong, 7.25 inches. I'm trying to make an inches part. And this tells us also that the width of the saw that cut it is 1/16 of an inch. So the idea is that the saw is cutting it and is also kind of just shredding some wood as it cuts. So this is 1/16 of an inch right here. And we want to know how much wood we're going to have left over. So really we're going to take the 3 feet, and we're going to subtract off the 7.25 inches as well as the 1/16 inches. So I'm going to do that subtraction maybe one part at a time. So let's start out with 36 inches minus 7, and let's go ahead, maybe we can change that to 16ths already. This will be 4/16 of an inch. So I just converted that 1/4 into 4/16. And I want to do subtraction. So to do that, I need to make some sort of fractional part here. So I'll borrow one whole thing, 1 whole inch from this 36 inches, make it 35 inches, and then now I've got a full 16 over 16 here. So I just took one piece, turned it into 16 pieces, and I'll subtract 7 and 4/16. And when I do that, I end up with 12/16 here, and then 35 minus 7 is 28. So that's that. And then let's go ahead and subtract that last 1/16 from what we already have. So this is the part that the saw just thread. It doesn't exist anymore. And I end up with 11/16, and then just the 28 here. So this is all my final answer. This is how long the board is that's remaining once you cut off that piece and you shredded away that little extra 1/6. So there's a nice little practical problem. So now you should be able to do pretty much anything you want with fractions, adding, subtracting, any sort of application. You now have the skills to do.